Welcome to discussion 23. In today's discussion, we'll focus on section 4.4 on L'Hopital's rule. And in this video, we'll do some examples involving 0 over 0 or these infinity over infinity indeterminate forms. So I want to begin by recalling what L'Hopital's rule says. And it says that if we have a limit as x approaches a of f of x over g of x, and this limit has the form either 0 over 0 or plus or minus infinity over plus or minus infinity, then the limit that we started with, we can evaluate this by doing the limit as x approaches a, and we take the derivative of the top, so f prime of x, over the derivative of the bottom, so g prime of x. So our original limit will be equal to this new limit as x approaches a of f prime of x over g prime of x, if this new limit exists or is plus or minus infinity. So this can often make evaluating limits of these indeterminate forms, these 0 over 0 or infinity over infinity indeterminate forms, a lot quicker. So let's look at some practice problems. So I want to look at problems 6 through 8 from worksheet 10, these 3 questions. And I want to first give you 6 minutes to try these. So 4, 3, 2, 1, pause it and try these for 6 minutes. Alright, so hopefully you did that. Hopefully you paused it and tried these for about 6 minutes total. That may not have been enough time to finish all of the problems, but hopefully to get started and think about some of the key ideas. Alright, so let's talk about them. So for 6, we have this limit, and I can get it started by plugging in. If I do that, on the top, I'm going to get 0 times something. That's 0. 0 times 1, actually, which is 0. On the bottom, I'll get ln of 1, which is also 0. Okay, so this is a form I can use L'Hopital's on. So I'll write equals. I'll write LH above the equal sign to indicate I'm going to do L'Hopital's rule. And I'll get the limit as x goes to 0, and I have to now do the derivative of the top and of the bottom. So on the top, I use product rule, and I'll get the first function times the derivative of the second, which is e to the x, plus the second, which is e to the x, times the derivative of the first, which is 1. And then for the derivative of the bottom, I need chain rule. I'll get 1 over the inside of ln, 1 over the stuff, times the derivative of that stuff inside, which is negative 1. All right, so now we have this. Let's try plugging in. So I'll get, let's see, 0 times 1 first, that's 0, and then I get plus e to the 0. And on the bottom, I'll have negative 1 over 1 minus 0, 1. Okay, so on the top, I end up with just 1. On the bottom, I end up with negative 1. And 1 over negative 1, that is negative 1. And that's my limit right there. So before we had learned L'Hopital's rule, to do something like this of the form 0 over 0, we would do it by simplifying our function. Usually we try to get something to cancel before we plug in. But this function we can't really simplify. So we really need L'Hopital's rule to be able to handle this. All right, let's look at problem 7. So we have the limit as x goes to 0 of e to the x over ln of 1 minus x. So I can start off by plugging in. So on the top, e to the 0 is 1. On the bottom, I have ln of 1, which is 0. So this, I can't use L'Hopital's on. In fact, this is not even an indeterminate form. It's 1 over 0. And our strategy for a non-zero divided by 0 is to take one-sided limits. Okay, so with this limit, even if I were to do stuff like simplify or whatever, it's just not an indeterminate form. I am not going to be able to do L'Hopital's on it. I don't need to. Let's do the one-sided limits. So the limit as x approaches 0 from the left of e to the x over ln of 1 minus x. And there's no issue with plugging in 0 straight up into the top, which gives me 1. On the bottom, I have to be more careful about it. I'll have ln, and I got to be careful about what type of number am I plugging in. So because x is approaching 0 from the left, that means x is a little bit less than 0. Think about something like negative 0.1. That's going to make 1 minus x be a little bit bigger than 1. It's going to be bigger than 1. Okay, but it's going to be getting very close to 1. So if I remember my graph of ln of x, so our graph of ln of x looks like this. and this x-intercept occurs at 1, I am now plugging in something into ln that's a little bit bigger than 1. So a little bit bigger than 1, that's this part of the ln graph. Okay, so this outputs are getting really, really close to 0. This is going to be really close to 0, but it's going to be a little bit bigger than it, a little bit bigger than 0. So I write 0 with a little plus sign here. Okay, and 1 over 0 with a little plus sign, that is going to infinity. Similarly, if I do the limit as x approaches 0 from the right of e to the x over ln of 1 minus x, there's no issue with plugging in 1 into the top. That gives me 1. On the bottom, when I do this, I'll now get ln of a number that is a little bit less than 1. A little bit less than 1. Okay, so this is going to be 1 over. If I look to my ln graph, if my input is something a little bit smaller than 1, but getting close to 1, the outputs are going to be getting close to 0, but they're going to be negative, a little bit less than 0. So I'll write 0 with a little negative sign. Okay, so this is 1 divided by 0 with a little negative sign. That's going to be negative infinity. Still going to be infinite because I have something like 1 on the top and it's getting divided by something super, super, super small. That's going to make the whole fraction get huge. But the top is positive and the bottom is negative. That's what makes it be negative infinity. Okay, so we got the one-sided limits. Thus, I can now say, I'll write these 3 dots, which mean therefore, our limit as x approaches 0 of e to the x over ln of 1 minus x, this limit, we would write it's d and e because these were different. If they had been the same, like they were both negative infinity, then I would have written that our original limit was negative infinity. But here, it's d and e because these are different. Okay, so let's move on to part 8. All right, so we have the limit as x approaches 0 from the right of e to the 1 over x over ln of x. Let's plug in. So if I do that, we'll get e to the infinity over ln of 0 with a little plus sign. So this is infinity on the top. And on the bottom, I'll get negative infinity. Okay, because ln of 0 with a little plus sign, we're letting the input get close to 0, but from the right. As that happens, the outputs go to negative infinity. Alright, and this is a form I can do L'Hopital's on. So we will write equals LH. We're going to do L'Hopital's. Alright, so I get the limit as x approaches 0 from the right. On the top, I need chain rule. This is e to the stuff. That derivative is going to be e to that stuff, but times the derivative of the stuff, the exponent, which is negative 1 over x squared. And on the bottom, I got to take the derivative of ln of x, which is 1 over x. And I can simplify this. This is the limit as x approaches 0 from the right. I'll still have a negative in front of everything. Okay, and I can cancel one of these x's in the x squared and this x on the bottom. And after I do a little bit of simplification with that, it'll leave me with just x like this on the bottom. Alrighty, and now if I plug in, we get negative e to the infinity over 0 with a little plus sign. So this is negative infinity over 0 with a little plus sign. So let's think about sign first. I have a negative on the top. The bottom is a little bit bigger than 0, so it's positive. So this is going to be a negative thing. Okay, and then ignoring the negative sign on the top is huge. And if you divide a huge thing by something that's getting really, really small, it's going to be even more huge. So this is still going to be some type of infinite thing. And we already determined the sign was negative, because again, top was negative, the bottom was positive. And that is our answer. It's going to be negative infinity.